everybody. I'm the Great Orbax, and welcome everyone to our first stream of the Guelph Physics Stream for 2021. And this week, this month anyway, we have an inspirational stream that we've brought to everybody in this time when I feel that so many of us could use inspiration. And what's more inspiring than looking up towards the stars? Yes, that's right. Not stars like me, the Great Orbax, stars like that exist out in outer space. And as you can understand, I don't know what we're going to be talking about tonight, so I'm making up a lot of stuff as I go along. But we have a lot of great guests tonight, and this is perhaps our most ambitious stream ever. For those of you who are brand new to our streams, thank you so much for joining us tonight. We're here at the University of Guelph. I'm here in a Stream Central, or as I like to call it, the room where not everything works all the time, but at least all the time, one thing isn't working. That we're going live, and it seems to be working well. So we are joined tonight by some incredible guests, and this is our most ambitious stream to date. I believe we have 6 guests on for tonight. Some of you are joining us from the RASC feed, and so thankful and so excited to have you here. Some of you are joining us from the Guelph feed, so excited to see you here. Make sure that you ask questions. You can put them in the chat, and we'll try to get to as many of them as we can. But I don't want to wait too long talking just about myself, because that's how I spend most of my days regardless. You know, let's see here. I wrote a little bit of a thing. Let's see. Tonight, we've assembled a panel of experts for a discussion about the study and the discovery of exoplanets. In school from a young age, we've learned about planets that orbit our sun. They're the ones in our solar system. But what about planets beyond the solar system? Are there any? Yes, there are. These are called exoplanets, and that's the introduction that I wrote for tonight's stream. Now, as we all know, I'm an incredible expert on anything to do with outer space. I've completed, probably the biggest expert in Guelph, I've completed 3 EVA ISS spacewalk missions on my ISS mission game on my Oculus. I've also watched 2 episodes of Disney Plus's The Right Stuff. And so, realistically, I probably know the most about outer space and space exploration than anybody probably ever living or who will ever live. But in lieu of that, we've assembled some people who can actually speak tonight about some incredible exoplanet missions. We're going to be talking about the James Webb Telescope. We're going to be talking about the Gaia mission. We're going to be talking about the Ariel mission. But before we go too much further, I want to introduce an alumni of the University of Guelph Physics Department. This gentleman is currently Professor of Physics and Astronomy Outreach at John Abbott College. He works with the Royal Astronomical Society of Canada in Montreal, and he is our gateway into these incredible experts for tonight's live stream. Please give a big streaming round of applause to our guest, Dr. Kareem Jabber.
If we have anywhere to go. We are having a blast talking about astronomy and space sciences these days, and I'm really looking forward to tonight's discussion.
So am I.
Ooh, I seem to be off screen a little bit. Hold on one sec. Let's see if we can fix that.
This is the type of exciting banter we often get on these live streams. 2 old men awkwardly speaking about the snow and why their cameras don't work. But don't worry, if you like this, you're going to love the next 45 minutes. Now, Kareem, you're not alone tonight. You've brought with us some expert panelists. Can you tell us who's going to be joining us?
Absolutely. So we are fortunate to have 3 wonderful researchers from IREX, the Institute for Research on Exoplanets. So this institute is based out of University of Montreal, right here in Montreal. And the astronomers and researchers and astrophysicists are both from University of Montreal, McGill, Bishops, and all over. hours talking about what he's done. We've got Dr. Jonathan Gagné, who is a relatively recent associate professor at University of Montreal and a scientific advisor with one of our outreach partners here, the Rio Tinto Alcan Planetarium. He is a researcher who works on both brown dwarfs and analyzing the stellar data from the Gaia mission. And those of you who are avid space enthusiasts know that back in December, Gaia just churned out 1.8 billion stars worth of data for all of the astronomers across the world to pour through. So Jonathan's going to give us a little window on that, I hope. And then leading the way is one of our really good friends at the RASC Montreal Centre, Dr. Nathalie Ouellette. She's the coordinator of the entire IREX Institute, and she is in charge of the education and public outreach for the James Webb Space Telescope here in Canada with the Canadian Space Agency. So Dr. Ouellette was our speaker at our keynote Townsend lecture a couple of years ago at John Abbott College. And while we don't get to be here in person to chat with them, we're looking forward to their virtual adventures telling us all about exoplanet research. So I'll turn it back to you and we can get started. And we have with us as well one of my former students who's a student at Bishop's University, Virginia Pacheco, and she's going to be joining you for the moderating of the Q&A at the end of the session.
Fantastic. Well, thank you very much, Kareem. Well, I mean, there's probably no reason to delay in this endeavor. Our speakers are going to give us a short presentation each to sort of talk about the missions themselves and their work. And then we're just going to get into a bit of general chat and conversation about everything. So we might as well get right to it. We're going to start with Dr. Jonathan Gagné, who's going to be telling us a little bit tonight about the Gaia mission. And so take it away.
Slides. Okay, so in the first slide, I'm showing you an image of the Gaia telescope, actually. So the Gaia mission is currently measuring the distances of stars with an unprecedented precision. And it has already published a few data releases that got us very precise measurements of the distance of more than 1 billion stars. So this is a really large number of stars to have a distance for. It's completely new. And just to put this in perspective, you can change one slide further. So I'm showing you an image of the Milky Way, which is our galaxy, with our location in the Milky Way. And the tiny white pixel that you see at the tip of the red arrow, that is the full volume for which we had very good distance measurements with the Hipparcos mission. So that was before Gaia. So you can barely see the volume with respect to the rest of the galaxy. It's just right around the sun. And so only for the closest stars, we had an accurate measurement of their distance and their velocities. So now you can go further one slide. And you can see in the red circle, that is the volume for which we now have very good distance measurements for stars. So it's not just the distance, actually. You also have the motion, the velocity in 3 dimensions for most of these stars. So it's really giving us a completely new window as to how stars move. So it's all very important information to characterize the properties of these stars. So knowing the distances allows us to know how intrinsically bright they are, not just how bright they appear. So it really helps us to understand better their properties. And knowing their motion allows us to better know where they were born and if they are part of groups of stars that move together. So I'm going to come back to this. Let's go one slide further and start the video. And I'm going to try to start it at the same time too. So what you see there is a visualization of all the stars in Gaia. So we start centered on the sun and we zoom out. And as we move further away from the sun, you are going to see the 3D effects of where the stars are actually located as we move away. And as we move faster and faster away, you're going to start seeing really the 3D structure of all the stars in our neighborhood. So this is completely new. We were not able to do this before. The best we were able to do was estimations of their distances, but that wasn't really accurate. And now we have really, really precise locations of all the stars in 3 dimensions. And now you can go further one slide. I'm going to show you a little animation if you start the video. Maybe you can let me know when the video started. Great. So we're going to zoom in to where the sun is. So the sun is centered at the center of the green circles. And this is the cleanest sample that was ever assembled of the nearest stars at about 32 light years from the sun. So this includes some massive stars and some brown dwarfs and some very low mass stars that are fainter. And what's really unique about this is that you can see, when I turned on the time, you can see where the stars are all moving with respect to each other. So there's some kind of what appears like random motion when you just look at a short time. But if you zoomed out and looked for much longer, they're actually all on different orbits around the Milky Way, which is something I haven't shown in the video here. But the result of this is that all the stars around us appear to be moving in random directions with respect to us, our position. So now you can go one slide further and start the next video. Here I'm showing you something really interesting, which is an open cluster of stars called the Hyades. And when I turn on the time, you're going to see where stars are moving. And something special is going to happen, which is that the Hyades stars all move together. So you can see there's some stars that are more diffuse around the Hyades that also move with the Hyades. So this is kind of a large structure, which we sometimes call a stream of stars that are moving together with the Hyades. And the reason why they all move together is that they were all born from one big molecular cloud, and they all kept the same average velocity with the original molecular cloud. So this remains true for some amount of time. After having gone around the galaxy many times, they get perturbed away and they get kind of randomized, and eventually they look like they have random motions. So this is really helpful to study open clusters and groups of stars that have the same ages. This is really important to understand the fundamental properties of stars. For example, the radius of a star, or just how its magnetic field evolves with time, for example. So the age of a star is something that is generally very hard to measure, but it's very useful. It's also useful when we find exoplanets around them. We usually want to know what age the whole system has. So this is really useful to better understand the system as a whole. I'm going to stop here, and if you have questions, don't hesitate.
Fantastic, thank you. Well, that's some pretty incredible data and some pretty incredible research. We might as well just keep rolling right through all the initial presentations, and then we'll discuss everything as a whole afterwards. Our next speaker is going to be Dr. Natalie Ouellette, who is going to be speaking about the James Webb Telescope. So we'll let Natalie take it away with that. And take it away. And take it away.
All right. Sounds good. This is a super interesting way to give a talk because I can't see what people see, so I have to trust that the system is working and everything. So I'm so happy to talk about the James Webb Space Telescope tonight. As Kareem mentioned, I'm the outreach scientist for the mission in Canada, working with the Canadian Space Agency and doing lots of collaboration with NASA. So to talk a little bit about the telescope, it is a NASA-led mission. So you might be familiar with the Hubble Space Telescope, also a NASA-led mission. And they also had the involvement of the European Space Agency. James Webb also has the European Space Agency, but this time, which is really special, the Canadian Space Agency is involved and a really key partner. And I'll explain some of the contributions that the Canadian Space Agency is bringing to the mission, especially in the realm of exoplanets. So you can go on to the next slide. And it's going to be a long movie, so I'll explain a little bit the whole mission during this whole thing. So we'll try to like press play at the same time. It makes me think of like in Jurassic Park when Dennis Nedry has to like time his watch and the computer at the same time. Bonus points if you have that reference. So let me know when you can start it. The movie? Movie started? It already started. It's not starting. Okay. So we have to wait a minute for it to start? Okay, I'm not sure if it started or not.
Maybe you can see the chat. He's saying that it won't play.
Oh, the movie's not playing. No, that is so sad. Okay, well, at least go back to the other slide, because then you can at least have an interesting visual. All right, so something that's very interesting, the James Webb Space Telescope, as I mentioned, it has a Canadian contribution, and it is much larger than the Hubble Space Telescope. Hubble has done some wonderful things in the last 30 or so years, but it's almost 2-3 times bigger, the James Webb Space Telescope. And you can see that it looks quite different from the Hubble Space Telescope. It is an open mirror concept, and it also is made up of several segments. So the mirror itself is 6.5 meters wide, and it's coated with gold. So actual gold, about a golf ball's worth of gold, is coating the entire mirror, 18 segments on it. And the reason why it's coated in gold rather than aluminum, which is usually the case for telescopes like Hubble, is that it doesn't look at visible light. It looks instead at infrared light. And gold is a very, very good material to reflect that infrared light. And the reason why we're interested in the infrared universe, there's lots of interesting things, galaxies and low mass stars, but exoplanets are very bright in the infrared. And also, some of the stars that are interesting to us in terms of having planets in a habitable zone that could have alien life potentially, or at least be habitable, they are also very bright in the infrared. So if you can move on to the third slide now with the big golden instrument on it, I can talk about the Canadian contribution. All right. So we have a very important contribution in Canada, and it's a 2-for-1 deal. So we really made it worth NASA's time. It is one guiding camera called FGS, or Fine Guidance Sensor, and one scientific instrument called NIRIS, called the Near Infrared Imager and Slitless Spectrograph. So the whole thing is really made in one piece. It's about the size of a washing machine, if you want to imagine it a little bit. You can also see a scientist in a clean room suit behind for scale. And this was really led by the director of the Institute for Research on Exoplanets. So it has a very strong bend in terms of trying to find exoplanets. But before we move on to exoplanets, I just wanted to mention a very important component in our instrument, which is the Fine Guidance Sensor. And so the other instrument, imager and spectrograph, it's going to be taking some images, but a lot of spectra, which, you know, all the great science is done there, but a lot of the like beautiful images won't necessarily be coming from this instrument. However, when you send something up into space, like the Webb telescope, it is always going to be slowly moving, vibrating, and it is trying to take really crisp, clear images. So in order to take very clear images, you need to be able to sort of counteract that movement of the telescope. And so the Fine Guidance Sensor is going to be able to point towards stars, bright stars, and sort of correct in the images for the movement of the camera, thus making for really, really clear images. So anytime you see a beautiful, clear image coming from the Webb telescope, no matter the instrument that took it, you can know that the Canadian Fine Guidance Sensor was a key part in making that image happen. It's what we call mission critical, and so it absolutely needs to work for the other instruments to work. There's lots of interesting technological feats that were involved in making James Webb. It's so big, it had to be folded up like origami, and it's on itself to fit into a rocket to be sent off. It's going to be located at 1.5 million kilometers from the Earth. So if we break it, we can't fix it. So that's why we have to make sure it works really, really well. So if you have any questions about all those technological feats, make sure to ask me afterwards. I can go into more of those details. But I want to end on the scientific mission of what we want to do, especially here at IREX. So if you can go to the next slide. There's supposed to be an animation here, so maybe try to click it. It's the transit spectroscopy one. See if it doesn't work. All right, so I'll have to explain it. I'll have to paint a picture with my words, essentially. So exoplanets, these worlds that are beyond our solar system, we find them, and then we want to understand more what they're made of, how big they are, how close they are to their star. But now we're getting to the point where we can start looking not only at the rocky planet itself, but the atmosphere around some of these rocky planets. And this is really amazing because when you're looking at the atmosphere of these exoplanets, it's the equivalent of the thickness of a peel on an apple. So it's really, really thin. And one of the ways that we discover these exoplanets is when they cross in front of their stars, the starlight is blocked slightly. It's sort of like an eclipse. It's the same concept. And so that's how we find a lot of these exoplanets. But as we know, the atmosphere is transparent or translucent. And so some of the starlight will pass through the atmosphere. And when it passes through the atmosphere, the starlight is affected by the different molecules and chemicals inside the atmosphere. They leave a print, like a fingerprint of the atmosphere in that light. And studying this light is called transit spectroscopy. You're taking the spectra of the light streaming through the atmosphere of these exoplanets. And James Webb, especially the nearest instrument, is going to be key in doing this. And so one of the things we're looking for in these exoplanet atmospheres are molecules called biosignatures. They're markers that let us know that potentially these exoplanets, these alien worlds, might be habitable or maybe even inhabited. So we're looking for molecules like oxygen, water vapor, methane, carbon dioxide. It's very complicated. Not just one marker will let you know if there's life or not, or if it's habitable or not. Sometimes it's a question of these ratios that are happening between these different molecules. But we already have lots of targets we're interested, including this TRAPPIST-1 system, which is a 7-planet system, all rocky, most of them about the size of the Earth. 3 of them are in the habitable zone of their star, which means that if there were to be water on it, it would be liquid water. So they're very, very interesting targets for the James Webb Space Telescope. And so lots of other things that we're going to be doing, but we're going to really revolutionize the world of exoplanets using this fantastic telescope, which will be launched this year, later on in October 2021. And I'm very excited to finally say it's going to be launched this year instead of like next year and like 3 years. So I'll end it here, but if you have more questions about Webb, feel free to ask me afterwards.
Oh, hey, audio's back. Fantastic. Thank you so much, Natalie. And for those asking, that is, again, Dr. Natalie Ouellette, the coordinator at IREX at the University of Montreal. We're getting lots of great questions in the YouTube feed, which is going to make my job so much easier tonight. So we're going to go right into Dr. Nick Cowan, have him do his presentation, and then we'll come back and we'll bring all 3 panelists right back up, and we'll just start going through the questions. Fantastic. Keep posting in the thread. Keep posting in the comment section, and we'll get to all those questions as soon as we can. And take it away.
All right. Hi, everyone. So my name is Nick Cowan, and I'm going to tell you about the Ariel mission. So what's with the name? Well, the original name, you can see it on this first slide. It's very awkward. It's the Atmospheric Remote Sensing, it's a silent S, Infrared Exoplanet Large Survey, silent S again. And so this was one of these horribly forced acronyms that astronomers come up with. So if you go to the next slide, this is the name we kind of went with, was Ariel. And we used this whenever we were talking to people, and then everyone actually forgot what the original acronym stood for because it was such a forced acronym, which was just as well. And eventually we did the same thing that they did with the laser and other famous acronyms. We just decided that it was a word in and of itself. So we dropped the capitalizations. If you go to the next slide, we dropped the capitalizations, and now it's just Ariel. So it just looks like someone's name, like a mermaid or something. And so that's the name of our mission. And so now we no longer ever have to tell people about the weird backronym that we designed. So what is this mission actually about? Well, if we go to the next slide, I'll start with kind of all the W's about it. So when 2029 is the current launch date. If everything goes according to plan, it's going to launch in 2029 on an Ariane rocket. This is a European mission. It's a European Space Agency mission. And so it's going to launch, I think, with another European mission, all encapsulated in the same rocket when it goes up into space. So that's the when. Where is it going to go? So this is the next slide. The Ariel mission is going to go out to L2, which is the same place where like James Webb goes. So this is a point that is farther away than the moon, in the opposite direction from the sun. And so this is a special point. The L stands for Lagrange, who's a French mathematician and physicist who kind of sorted this stuff out like hundreds of years ago. And so it's a point where you can basically be stable. So if you put a spacecraft out at this special point L2, then as the Earth orbits around the sun, the spacecraft is pretty content to just stay where it is. So this is lovely because it means that Ariel is not orbiting around the Earth. It's really annoying to orbit around the Earth. So the Hubble Space Telescope that you're all familiar with is in a low Earth orbit, which is great because the astronauts put it there, and it's the furthest, it's the best the astronauts could do. But it's super annoying because it means that you're zipping around the Earth very, very quickly. So every like half hour to 45 minutes, the Earth gets in the way if you're staring at some distant astronomical object. So if you want to be able to continuously stare at objects for hours and hours or days, you can't do it from a low Earth orbit. You need to go farther away. And so this point L2 is convenient because you don't have to use much rocket fuel to stay there. And you can see the orbit of Ariel is this kind of like loop-de-loop near that L2 point. And that's, you don't want to be exactly in the shadow of the Earth because otherwise your solar panels and stuff don't work. So that's the basic where. So now if we go to the next slide, the who. So on the left is kind of one of these horrible organizational chart type things. And then you might have to there might be some animation. So try clicking again and let's just see if something shows up. So basically the left is an organizational chart that actually, if you stare at it, it's actually, the top part is actually kind of a sketch of what the spacecraft looks like, sort of. And then you see all these little flags, and most of the flags are European countries, which makes sense because it's a European Space Agency mission. And so every country is contributing various nuts and bolts and screwdrivers and detectors and stuff like that. We do hope that eventually Canada can contribute something, not something grand like a big golden washing machine like we did for the James Webb Space Telescope, but maybe something small like a few $1 million widget that plugs in someplace. That's the sort of contribution we're hoping Canada will eventually do for the Ariel mission. Hopefully, at this point, there's a picture of the principal investigator of the Ariel mission. Her name is Giovanna Tinetti, and it's worth pointing out that you can count, I think, literally on one hand, the number of space missions that have been led by women. And so I'm super proud to be part of a mission that is led by a woman. So Giovanna is an expert on transit spectroscopy, which Natalie talked about before. So she had done a lot of transit spectroscopy with instruments on the ground and mostly instruments in space like the Hubble Space Telescope. And then she kind of dreamt of doing something bigger, like let's do a special mission that is specialized for just transit spectroscopy. Okay, next slide, please. So now we get to the what, like what the heck is this mission going to do? Well, I haven't emphasized it very much because the short answer is we're going to do the same stuff as what Natalie said we could do with James Webb. And I'll get to the weirdness of that in the next slide. But let's start with the what. So the what, that basically we can do three sorts of things with Ariel. First of all, we can look at transits. That's when a planet passes in front of the star. Natalie talked about that. You filter some of the starlight through the atmosphere of the planet, and you learn something about what molecules are in the atmosphere of the planet. Then if you click again, now there should be a box around the eclipse. Okay, so the eclipse is when the planet passes behind the star. So so when that happens, the planet actually disappears from view temporarily. And so you can actually measure light that was being emitted by the planet if you look just before and just after the eclipse. And so you can either see well, in the case of something like Ariel or James Webb for that matter, what you're seeing is basically the heat signature of the planet. You're seeing the thermal radiation from the planet. You can again do spectroscopy, and so you can again learn about what molecules are in the atmosphere of the planet, but you can also learn something about the temperature structure of the planet, like how hot is the planet? Does it get hotter as you go down? Does it get cooler as you go down? Things like that. You can also make cool two-dimensional maps of the planet based on these eclipses. And then if you click forward again, now the box should be around the phase variations. So this is as the planet orbits around its star for a full orbit. You're at various points you're going to be seeing the day side, the night side, and the like terminator, like the day-night boundary of the planet. And of course, for a planet like the Earth, this would be this would be a really silly thing to do for two reasons. One, because you'd have to wait a year for the Earth to orbit around the sun. And two, because frankly, the day side and the night side of the Earth don't look that different at thermal wavelengths. That's because our planet, daytime, nighttime temperatures are a little bit different. But, frankly, if you're like in the ocean, the water's the same at like day and night, and most of our planet is ocean. So if you're looking at the Earth from like outer space, daytime and night side version of the Earth don't look that different in the infrared. But it turns out that most of the planets that we're going to hope to characterize with both James Webb and Ariel are orbiting their stars very, very closely. So they go around their stars in like a matter of days. And so in that case, that means two things. One, you don't have to stare at it for a year. You just got to stare at it for a day or two. And two, because it's so close to the star, the day side and the night side look very, very different. And so the day side can be hundreds, even thousands of degrees hotter than the night side. So that makes it kind of scientifically compelling. Okay, last slide, the why. So why are we doing this? I told you this thing's going to launch in 2029. It is literally, not literally, but it is figuratively a scaled down version of James Webb. So why in God's name would we put up something less performant than James Webb almost 10 years after James Webb? And the answer is a little bit subtle, is basically Natalie kind of planted the seed for this. She mentioned there's all this cool astrophysics you can do with James Webb. And indeed, that's the problem, is that other astronomers, other than those of us who do exoplanets, are going to use James Webb. They're going to want to look at galaxies and all sorts of stuff I don't care about. And so the point of Ariel is since we couldn't commandeer the entire James Webb mission, we decided to build our own mission. It's scaled down, but it does 100% exoplanets all the time. So that's the sort of tongue-in-cheek answer, and that honestly, that's actually a big part of it, because with the James Webb mission, we hope to look at maybe dozens of planets, and we'll do it in gory detail because the observation is going to be so good. But with Ariel, we're going to do 1,000 or more planets, and so we're going to do a lot of planets, and so that's kind of the goal of Ariel. We want to let James Webb focus on the small temperate planets that Natalie mentioned that might be habitable, might be inhabited. That's something that only James Webb can do. We have no missions on the horizon that can do that other than Webb. And then let Ariel clean up on all the bigger planets and just study like how their atmospheres work and that sort of stuff. Okay, I'm going to leave it at that, and I'm happy to field more questions.
This muting the microphone thing's killing me tonight. So thank you so much, Nick. I really appreciate that. And this is fantastic. We have such great information coming in from such great experts. And I was warned that we might attract a very specific kind of astro fan base tonight. And the YouTube section is rife with astro questions that are coming from all over the place. So we might as well bring our three presenters back in. So we'd ask them to come back in if we could. And we'll have a discussion with them about what's actually going on. Now, I think, Jonathan, we could get your camera back on. We could bring you back on.
Can you see me?
I cannot. It's coming in. You're a mystery.
Okay.
I just see a big circle that says Joe right now. Oh, there. And we'll leave you to phase in as time goes on, I suppose. But at least we've got your voice. You're there, am I correct?
Yeah, I'm there.
Fantastic. Well, you've got the first set of questions, so we might as well just go ahead and ask ask our questions into the void here so that we can see what's going on. We had some very specific questions about Gaia that came in pretty early, and I guess one of the biggest questions would be, how does Gaia actually determine the 3D position of a star?
Yeah, so that's a method called the Trigonometric parallax. So basically, as the Earth goes around the sun, the position of a star wobbles a little bit. So it's really like if you hold an object and then you move from left to right, the object is going to appear as if it wobbles with respect to very distant objects. So Gaia has a frame of reference that is made up of a very large number of super distant galaxies called quasars. And that is kind of a fixed background. And then as the Earth rotates around the sun, and Gaia is also at the L2 Lagrange point, much like JWST and Ariel is going to be. So it goes around the sun with the Earth. And as it does so, it sees the wobble of the stars. And the more a star wobbles, the closer it is to us. So that gives it a distance. And if you have a distance as well as the position in the sky where the star is, you can work out the 3D position.
Exciting. Well, that's pretty interesting. When you were showing your slides there, we have a question coming in from RP on our YouTube. When you were showing the slides there, they show that the Milky Way galaxy from above, some were going inward towards the center, some were going outward and spinning around the other way.
Wait, can you repeat that? Some of what
Sure.
is going? Oh, yeah, some of the stars, you mean?
Yeah.
Yes. Okay. So that is because I was showing the velocity of the stars as seen from the sun, and the sun is also going around the galaxy. So if I was putting myself really outside the galaxy and looking at all stars rotating, they would all pretty much go in the same direction, but the sun would also go in that direction. But what I was showing here is where the stars are headed if you are on Earth looking at them. So some of them are rotating a little bit slower, some of them a little bit faster than the sun. So they appear as if they move in all directions pretty much randomly.
Right. Well, there's a slew of questions coming in on the James Webb Telescope. A fan favorite out there. I don't know if it's because we're so close to the launch date coming up or what, but we'll just get into some of these. Let's take a look here. What's one of the best ones? Oh, this one wants to know what the name of the presenter was. They're such a knowledgeable speaker. That's good information to throw out there. So this one's coming in from Brian. What are the backup features of the James Webb Space Telescope, given that it's too far away to service, unlike Hubble?
So there are a lot of redundancies that are put in. So in the video that unfortunately couldn't play, it was showing the deployment of the telescope. And there's close to 200 little movements that need to be done in order for the whole thing to be deployed. But there's always a redundancy. If something were to break, there's like a backup system that can still deploy that. There isn't infinite redundancies though, which is why it's being so thoroughly tested, and why there have been delays in its launch a number of times. In terms of its instruments, not all the instruments are mission critical. FGS is mission critical. If it doesn't work, then the images we're taking are going to be very blurred. So that's going to be a problem. But the other instruments are fairly independent from each other. And so if one instrument fails, that's a big bummer because that instrument had a specific role and certain things that only it could do. But at least the other instruments could then take over, do their thing. And there's the bets are out, but a lot of people think that MIRI, which is one of the instruments who's looking at a different kind of wavelength, is probably going to be the first one to have issues because it needs to be cooled even colder than the ambient, really cold space, empty space and universe. And if that ever happens, then the other instruments should be able to keep going. So there is some independence between the instruments, at least so that if one fails, the others can keep going. But FGS is really mission critical.
Mm-hmm. It's one of those interesting things. I'm old enough to remember when the Hubble first went up and we had those issues with the alignment of the Hubble in the first place. And I guess there's always the fear that could happen a second time around.
Definitely, and I think that's why people have been so cautious with the testing.
Sure.
Yeah.
For sure. Well, I mean, speaking to the James Webb still, I mean, one of the questions that we're getting a lot of in the chat here is, why does the James Webb have to orbit so far out?
So Nick touched on this quite a bit. He mentioned that Ariel is also going to be at L2 at 1.5 million kilometers. And it's because the Earth is in the way. So if you have something going around the Earth becomes a big hindrance. But when you have an infrared mission, there's like an additional layer to that. The Earth and the Moon, they are at the right temperature to really start glowing quite a bit in the infrared. So they're essentially causing their own light pollution. And if you're putting a $10 billion telescope in the middle of a city with a bunch of light pollution, that's kind of wasted money. So typically when we have infrared space missions, so we think of Webb now, but we had Spitzer before and Herschel, we will send those further out so that they don't have to deal with that sort of infrared glow from the Earth and the Moon system.
Thank you very much. Well, let's let Nick talk about something here for a minute. We got a question that came in from one of our Instagram followers. They wanted to know what your favorite exoplanet system is and why.
Oh boy. This is not really an Ariel question, but so the TRAPPIST-1 system is one that I get really excited about. So the TRAPPIST system was recently discovered, and at first it already seemed pretty exciting. It looked like there were maybe 4 planets, all about the size of the Earth, orbiting, decent distance away from a very, very dim red star, one of these red dwarfs, ultra cool dwarf. And then it got better because then they kept following it up, and they found that there were many planets, and in fact, 3 of the planets around the system are actually in the habitable zone of their star. Yeah, I mean, it's just kind of a mind-boggling system. So there's like so much goodness packed into such a small space, because the entire TRAPPIST solar system would fit very easily inside of Mercury's orbit, right? Like the whole thing is super, super compact. And it's very, yeah, it's just, these are planets that are, the same size as the Earth, roughly the same temperature as the Earth. And with something like James Webb, we could actually try and sniff out molecules in their atmosphere and see whether they've got carbon dioxide, water vapor, and gosh, maybe like ozone or methane or something like that. So yeah, so I don't know. TRAPPIST-1, if I could only pick one, I think that's a pretty good one right now.
Well, this kind of speaks to something that you mentioned in your talk. You mentioned this idea that some of these might be habitable. Is this sort of the end goal for all of these missions, is to find habitable planets, to find places where either we could go or where there may already be life?
So, I mean, to be clear, the only of the missions that we've talked about tonight that can actually find planets is the one that Jonathan talked about, Gaia. And Gaia is not super well suited for finding planets that could have life on them. So planet hunting is like a whole other ball game. But the planets, so the reason we all care about something like Gaia is because it, as Jonathan mentioned, it tells us very precisely the properties of the stars. And that turns out to be very important for understanding the planet. So if we want to know how massive a planet is, how big a planet is, we only know those quantities as well as we know the properties of the host star. So that's important. If we're gonna try and characterize the atmosphere of one of these planets, we need something like James Webb to do it. Even James Webb may not be able to do it. It's probably going to give us tantalizing hints, right? It's going to be enough. I'm willing to predict there's going to be front page of the New York Times above the fold claims of, hey, this is a planet that could harbor life. This is a planet that harbors life, much like we've seen in recent months with the phosphine on Venus, right? I mean, there will be these claims, but no one will be willing to bet their firstborn child that they're actually seeing signs of life. And so I think there's going to be subsequent missions that will be much more designed from the ground up to search for biosignatures. None of the missions we've talked about were designed from the ground up for doing that. I mean, heck, when James Webb was originally envisioned, people don't even really know that exoplanets were out there, right? It was kind of like, as they worked along, they're like, oh, wait, these exoplanets are out there. They're really cool. And then René Doyon, the PI of the NIRISS instrument, had the vision to be like, oh, let's design an instrument from scratch to do this well. And so there's this one instrument that's well designed, and people have kind of retrofitted all the instruments to be able to do it decently well as well. So, but we've never built a space telescope from the ground up with a single mission of like, let's go find life. That's going to be kind of the next generation space missions.
Well, and it's kind of exciting here. We've got 3 projects that are in like very distinct phases. We have one that's in space, one that's about to launch, and one that's being prepped. To talk about the preppers going into Ariel, how does that work from the ground up? You've designed a system. Are we now building instruments? Are we building a ship? What phase are we in now, and what's involved in that?
Yeah, so the Ariel mission just in November of this past year went through what was called mission adoption. So basically, before this, a mission gets accepted, right? So people choose a mission, but then there's actually that just gives you millions and millions of euro in this case, and another year or two to then refine your plans and basically publish this really thick, many 100-page, very technical book. That's all you're doing. You're not building anything at that point. You're just paying engineers a lot of money to think really hard to make blueprints. So that book is called the Red Book. There's a yellow book, then there's a red book. That red book it just came out, and it was the European Space Agency basically gave it the thumbs up. So then that mission is adopted, and that means that now starting in 2021, people can start building the instruments and actually start assembling the stuff. And then from there to launch, as you saw, is like almost a decade, right? And the thing won't launch till 2029. So it takes a long time for the reasons that Nathalie mentioned, right? I mean, once you're sending something out to L2, we've never sent an astronaut that far away. It's like beyond the moon, right? So even if we could go back to the moon, we can't get ourselves to L2. And so like if something goes wrong, it's over. So you have to just like make everything absolutely foolproof and make sure it works.
Fantastic. Well, we're being joined here tonight by members of RASC, and we also have a new panelist who you might see has been floating around in front of other people's panels until she's found a spot in the corner there. It's Virginia Rufina Marquez Pacheco. She's joining us from Montreal as well, and she's got some questions to ask our panelists as well. So we'll throw it over to you.
Yes, hello everyone. Great talks by all 3 of you. So we got some questions, and I think I'm going to start with a question for Jonathan for the Gaia mission. So first question would be, since the Gaia data of 1.8 billion stars has become publicly accessible last month, are there any citizen science projects being launched for amateur astronomers and enthusiasts to help comb through the data?
Oh, that's a good question. I'm not aware of one that is focused especially on Gaia data. However, I'm aware of one that is focused on finding brown dwarfs in the solar neighborhood that has some overlap with the Gaia mission. It's called the Backyard Worlds mission. And basically, it aims at a kind of a similar goal, catalog all of the brown dwarfs in the solar neighborhood, but those are only visible in the infrared light. So you cannot see them in visible light. And Gaia is a telescope that works with visible light. So that citizen science project is working with infrared surveys to kind of patch up the blind spots of Gaia. But there would actually be some really nice science that could be done with citizen science on Gaia, especially with the upcoming data releases. So Nick mentioned that we are going to be able to discover some new exoplanets in Gaia. And that is basically because if you have an exoplanet that is massive enough to tug its star very hard as it orbits it, you can actually see the center position of the star moving around as the planet orbits it. And I suspect there's going to be so much data and so much analysis to be done to discover all of these exoplanets that it would be really ripe for a citizen science project. But it's not out yet. What will allow us to do this is not out yet.
All right, thank you very much for that answer. We have, speaking still about the Gaia project, we have a question from Emily. Can cluster stars share exoplanets?
Oh, that would be very unlikely. If I understand the question well, that's as if, say, 2 different stars from the same cluster that are moving together would exchange a planet. That would be extremely hard because in practice, there is a lot of empty space between each. You would need to eject an exoplanet exactly in the right direction and not too fast so that it would arrive near the other star and just enter an orbit around it. It's such an incredibly tiny window in terms of direction, but also in terms of the velocity at which you would eject it. So we don't even have very good statistics on how often exoplanets get ejected. But let's say we're very generous and a lot of them get ejected. It's still very unlikely that stars would exchange planets. I would not expect it to happen, probably even once over the age of the galaxy, I would bet.
Sounds like a very rare occurrence.
It would be.
Okay, so I'm gonna hop over to Dr. Ouellette. We have many questions for JWST, of course. One of the questions would be, will the data from JWST be accessible like it was for TESS and Kepler, or is it more closely directed to specific research?
So it's going to be a little different from TESS and Kepler, but a lot of it is going to be accessible. There's going to be what we call a proprietary period. That means that the data will be private for the people who requested it for some period of time. But when you're doing your request, you can choose to waive that right and then make the data immediately available for everyone, or shorten your period. So that will make it immediately available. Whether or not it's immediately available in a way that's useful for everyone, that's a little bit different. So there are some telescopes. One that I can think of is the Sloan Digital Sky Survey. It's not a space mission. It's on the ground, and its whole reason of living is just surveying the sky over and over and over again as much as possible. And they really want to make that data usable by the public. And one of the reasons is because it's really competitive to try to get time on these telescopes. You get what we call oversubscription rates of like 5 or 10. That means that you have 10 times more people asking for time on these telescopes than there is time to give out. And sometimes there are some telescopes that are private. You can only have access to it if you're in a country that owns the telescope or you're at a university that owns it. And that's sort of sucks a little bit. So you have some missions like the Sloan Digital Sky Survey, eventually the LSST, which is now the Vera Rubin telescope, which is in construction in Chile. They really want to make the sky accessible to everyone, the public, but also astronomers that don't necessarily work at institutes that have easy access. So there are some missions that have really that in mind. They take very sort of broad general data and it can be applied to whatever project you're working on. Because James Webb is more specialized, you're looking for like a specific instrument to do a specific thing. It will eventually be public, but whether or not a person who doesn't have the background can use it, that's a different question. But we do want to make all James Webb data eventually public so that it can benefit the wider astronomical community.
Thank you very much. And I guess going on the theme of making data available, I am going to turn to Dr. Cowan and ask you the same question. Are there plans to make the Ariel data publicly available?
Yeah, so the Ariel data, Ariel is actually a lot like the Sloan Digital Sky Survey that Nathalie mentioned. It's just a survey. There's no, people won't apply tiny fraction of time where people can apply and get time, but mostly the telescope, we're just going to have a plan for it before it launches, and we'll just execute the plan. And the plan is to just look at all the brightest stars that we know have planets around them, ish, and get transit spectra and get eclipse spectra, and then do phase curves for some of them. So that's basically what we're going to do. And those data are going to go public as soon as the team can what's called reduce the data, which is like trying to take the data and clean it up into a form that's like sort of human readable. So depending on the exact data we're talking about, that might take a matter of months, something like that. And so the data, a lot of the data will go public within a few months. Once we get our data pipelines, like kind of the software we use to try and massage the data and make it like, take all the cosmic rays and all the weird electronic noise and stuff. Once we figure out how to do that better, later on in the mission, then the data will go public maybe like weeks after it's taken. Like basically we bring it down to the Earth, and then it goes to some big ESA center in the Netherlands, and they do stuff to it. And then it goes public and anyone can have at it. And so they're, yeah, I mean, basically, you know, if you're interested in like the early 2030s will be the time to take a look at the Ariel data. You'll be able to see the spectra, and depending on how much molecular spectroscopy you know, you might look at it and be like, hey, cool, I see a molecule. Or more likely you'll be like me and be like, and then you'll hand it off to like a PhD student and hope that they can publish a paper on it.
Okay, thank you very much. You also actually mentioned something about cleaning up the data for the spectra, and we actually have a question from Alicia from John Abbott College, who is asking, when looking at light through the atmospheres of exoplanets, how can we tell the light hasn't been modified by interstellar gases?
Oh, that's a great question. Yeah, I mean, basically the short answer is that okay, so you're looking at a star, right? And you're right, the star is far away. So there's in principle, there's lots of junk between you and the star. In practice, space is pretty empty. But yeah, in principle, there could be stuff. But the key is that the stuff that's in between you and the star is there like all the time. And so when you look at the star before the planet, you know, goes in front of it, and then you look at the star after the planet has gone in front of it, that gives you kind of like a control, because you're looking at the same star through the same interstellar junk, should there be any junk there. And so when the planet is in front of the star, you're still looking at the same star through the same junk. And now the only thing that's changed is now some of that starlight is being filtered by the planet's atmosphere. And so it's what we call a differential measurement. And that's the key. That's why we can basically, if you think of it as like a division or subtraction, you can basically like sweep away all of the complexities of like how weird the star looks, the fact that there's undoubtedly stuff between you and that star, and none of that matters for these measurements. Thankfully, it all gets kind of subtracted out. So we don't even have to clean that up ourselves. That's something that nature does for us with this kind of event, like these occultations, when one object passes in front of the other. There's kind of a magic couple of hours when things are different, and if you can take advantage of that, you're golden.
So when you're looking at extrasolar planets, we have a question here. What would the optimum inclination of a planet need to be such that it would help determine its atmospheric composition? So I guess I'll direct this one to Dr. Ouellet.
So they're asking what the inclination of the system, the optimal inclination of the system?
Of a planet. So I from what I understand, they're asking, if you have a planet passing in front of the sun and the atmosphere is a really thin layer, like you explained, is there an optimum inclination of the planet to view its atmospheric composition?
So essentially, one thing that's important when you're doing transit spectroscopy, if you want to spot any kind of planet through a transit, that we live in a 3D universe, and so you have all of these systems that have all kinds of different inclinations. You need to have an inclination such that the star is visibly passing over the disk of the planet is passing visibly over the disk of the star. So you have some leeway in terms of the inclination of the system, but you're assuming that the atmosphere is going to be like relatively symmetric around the star. There's no really inclination to like the orbital axis of the star, of the planet, that should really affect. It's really the inclination of the entire system itself. But as long as you see that transit, you should be good.
Thank you very much for that answer. I believe that it's soon time to bring in the next person.
Sure, fantastic. Well, if we can get an opportunity here, I'd like to bring, well, thank you. First of all, thank you very much, Virginia. Everybody out in the stream world, give her a big round of applause. Thank you so much for joining us. Those are some incredible questions for our panelists. We have one of our students here from Guelph Physics that we'd like to bring in, Mel Hudekok. She's our roving reporter on the ground, as we typically like to call her. Is she there in the stream section? Do we have a patch in to Mel yet? Give me a thumbs up. He's counting down on his fingers. He's showing me 5, 4, 3, 2, and I got a thumbs up. Does that mean that Mel's in the scene? All right. How's it going, Mel?
Hi guys, I'm doing good. How's everyone? This is so interesting. I'm having a lot of fun.
I'm so excited you remembered to turn your microphone on this time. That's been, we seem to have swapped spots from our usual Guelph Physics live stream where you have your mic off and I have mine on.
I learned from your mistakes.
Fantastic. So Mel, you've been watching this all night long. I'm sure you have questions for our speakers, or what do you have to add to this conversation?
So I think, like, as a physics student myself, space has always been a really cool topic to talk about and to listen about. So I'm wondering what sparked your interest in space and devoting your career to it. So I guess this can be a question for all three panelists.
Well, we might as well start in order. Do we want to start with Jonathan?
Yeah, sure. That's a very good question. I think it's just simply something I've been really interested in since I was young. So basically, I was really fascinated by some books that talked about black holes and galaxies and all generic stuff about space. And I found that really, really intriguing. And I had a drive to really understand how nature works. And that seemed like a pretty natural path to explore this. So yeah, I think that's what drove me there.
That's awesome.
Natalie?
All right, sure. I guess I'm up next. So it's pretty similar, actually, of an answer. I've always loved nature and space and science. I was brought up in a household that had a lot of science in it. Both my parents are engineers, and I'm sure that was very influential. Also, the fact that we had a mother and a father who both had a STEM job showed us that essentially, both could do the job, and we didn't have any problems with that. I've always really loved observing nature. I know that a lot of people, they like trying to figure out how stuff works by like building stuff or tearing stuff apart, but I've always really been more of a person who likes to observe how things work very passively. And I really enjoy phenomena that showcases how much more massive and imposing nature is compared to us. So if it wasn't going to be space and astronomy, it was probably going to be atmospheric science, or like geology, volcanoes or tornadoes or hurricanes or something like that. I really, really like natural disasters. I don't know what that says about me, but anyways. So I really like that kind of stuff. But if you go even bigger, you go into space. Something that I love about astronomy is the stuff that we study doesn't care at all about us. We don't have an effect on these faraway planets and galaxies. So there's like a weird kind of purity that you're really examining this thing and have no effect on it. And there's few things in life that you can do that. Even like if you're studying an animal and its ecosystem, you're in its ecosystem, you're affecting it. Even in fundamental physics, once you observe an electron, you've just made it choose what its momentum and its position is. Like you've like forced it to settle on something. So you're affecting what you're examining. You're part of the experiment. But in these faraway fields of astronomy, you're not. So there's like a certain kind of interesting purity to that study, I find.
Is there something kind of mind-blowing about looking into the past?
Yeah, definitely. And for exoplanets, it's a little bit less, like you get less vertigo because you figured, it's 40 years ago. What could have happened in the last like 40 years? It's probably fine. But
Ghostbusters.
Yeah. But so the secret is that even though I am at the Institute for Research on Exoplanets, I actually do research on galaxies. And so I'm looking at these things as they were millions of years ago, sometimes billions of years ago. And so for those guys, I really don't know what state they're in right now. So if you think about it too long, then you start getting a little bit of vertigo, definitely.
All right, it's my turn for my history of how I came. I don't know. I think I'm pretty similar to Nathalie. So I grew up in a household with my dad was an engineer and my older brother was an engineer. You know, when I was a kid, I wanted to be an astronaut like everyone else. I definitely did not dream of becoming an astronomer. That sounded like, I don't know, that would have been like a real consolation prize maybe for not becoming an astronaut. But yeah, I figured I was going to be an engineer. I thought I was going to build rocket ships or something cool like that. And then at the very last moment before going to university, some friends convinced me that engineering was boring and that I should instead study physics. And they told me that, and I quote, "Girls will think you're more interesting if you do physics." and so as funny as that is, the irony is that it worked out because I'm now married to another physics prof who studies black holes. So it was highly improbable, but it turned out to work. So yeah, so I went into physics for the ladies apparently, and then sort of like tried a bunch of research projects, and none of them really were my cup of tea. So it's sort of a process of elimination. And by the end of my physics degree, I knew I didn't want to do like straight physics. So like Natalia, I actually applied into a bunch of different things that were all sort of physics adjacent. So like geophysics, atmospheric science, oceanography, astronomy. And so maybe unsurprisingly, I ended up as an astronomer. I got a PhD in astronomy, but studying planets, which have oceans and atmospheres and all that stuff. So I kind of got my cake and eat it too. So I'm pretty happy. And I'm married to another physicist, so it all worked out in the end.
I like hearing that physicists can find love. That's very reassuring. I like that. Okay, so and then I guess I'll wrap it up with like a final question, again for all three of you. But I think some people's perception of research is that it's always boring and that it's kind of, you're doing the same thing every day. What would you say is your most exciting day in research? And I guess we can start with Dr. Jonathan as well.
Cool. So I guess the most exciting day wouldn't be the same for every person. So there's several types of days that are exciting to me. Not all days as a researcher are always exciting. So there are the moments where you write grand applications, which are a little bit less exciting. But there are moments where I really love, like coding or just making figures with the results you have. I really love these moments, like putting everything together and bringing out the general picture. And then there's the much more obvious one, which is going at the telescope and observing, because depending on what kind of science you do, you might still do that. So going to places like Chile or Hawaii and seeing the amazing landscapes and then observing with your hands on the computer that controls the instrument, that's pretty exciting. So it's so varied. It's very, very different from day to day, and that's something I really like. But there's different parts that I really enjoy.
So I agree. I think that often when I do these kinds of things, especially with younger kids, and they want to ask me, like, what does an average day look like for you? It varies so much from day to day. One thing that's consistent is that, like, I'm stuck doing a lot of emails or something like that, and these days a lot of Zoom meetings, but it like varies so much from day to day. Some of the exciting things, like the obvious answer that comes to mind is stuff related to travel. When I get to go to a telescope and then control a 10-meter telescope in Chile or something like that. And that's really amazing. That's really fantastic. But they're like little joys too. If I've been working on like an algorithm that I've been coding and I just keep getting an error and it's not working, and like I've been working on it for like 3 weeks, and then finally I find, a semicolon that's at the wrong place, and then I erase it and everything. Just that little joy that finally everything works, and then you get your plot out, and then you see your plot and like it makes sense, and you can interpret it in an interesting way. That's something that's exciting. And basically any time that I get to talk about space to people is something that I find super exciting.
Natalie's example of like, managing to make a plot that works is sort of a perfect segue, because for me the thing that gets me the most stoked is when I have a student who comes to my office, shows me a plot. There's a student doing research with me, And I look at it and say, no, that can't be right. Like, go back, like run all these checks. And then she goes back, she runs some checks, she comes back. No, this is what it looks like. Here are the checks. And then I look at it and I'm like, shit, like I'm wrong. Like, I just don't understand how the universe works. The universe chooses to work in a way different from the way I wanted it to work. And my student just proved me wrong and just discovered something new. And then I'm like, that's cool. Like, okay, let's write a paper. Like, we just learned something. And that happens, like those kinds of moments that are just like completely like, you know, in your face like that happen, you know, every few months or something, if you're lucky. And those are like, that's what I live for, is basically those moments where you just realize that you just learned some new little nugget about how the universe works.
Yeah, for sure. I mean, even when I'm just solving some of my undergrad questions, I have the same excitement. So I can imagine it's tenfold for all of you guys.
Do you have any advice for, we get a lot of undergraduate students who watch our streams, and as people researching in the field now have gone on to make huge contributions, do you have any advice that you could give our students like Mel here who don't know what's going to happen with their futures?
Well, no one knows what's going to happen with their futures. Well, welcome to the club. I mean, I think one important thing to mention is that research is very different from coursework. And coursework, I'll use a climbing analogy because I'm a rock climber, and coursework and most of schooling is a lot like going to a climbing gym, and some person's like drilled a bunch of plastic holds onto the wall, and it's super contrived, and you just do it, and it's just to see how fit you are. And that's sort of what homework is in university. Research is more like someone plunks you down in the middle of a forest and you can kind of make out some peak yonder through the woods, and someone says, head up there and try and climb up that. And then you just start wandering that direction. You're bumping into trees at first and you need a compass, and then you get to a river, and then you report back and say, but professor, there was a river. And they're like, what? There's a river in that direction? Cool. How can you, let's see if you can get over the river. And then eventually, you know, maybe at the end of a career, you've made it halfway to the mountain. And it's just a lot of like figuring out new stuff and encountering problems that you've never even thought of. And so that it just feels very different from doing coursework, which always feels this contrived thing where like there's a right answer, and if you don't get the right answer, you feel bad. And in science and in research, there's rarely a right answer. There's just like making progress. That's all you can do.
So I just learned that Nick absolutely doesn't respect me, climber, because I only go to the climbing gym. I don't go to the forest. I just go to block shop in Montreal and do my bouldering. But anyways, to get back to non-climbing advice, to more career advice, that's absolutely right. That's always my number one advice, not the climbing thing. That research and coursework are very, very different. And just because you have a hard time with coursework doesn't mean that you are not good at research. Just because you don't have like a 4.0 or a 4.3 or whatever doesn't mean that you're going to be bad at research. It can be very surprising. So if you're not getting those top grades, don't let that deter you. What you should really be doing is trying to get research internships during the summer, during your semester, doing like an honors thesis, whatever, a research project. And if you are interested in space but don't exactly know what you are interested in, try a bunch of different things. You don't have to lock yourself into like exoplanets only or galaxies only. That's what your undergrad is for, essentially. Just try different things, but try to do research as early as you can, because you might be better at it than you think. And it's good to know if you enjoy get out of undergrad, that's what you are doing. And so it's not as fun if you are like 3 years into a PhD and you realize, wow, I really hate this. So you better get that out of the way and do research as soon as possible.
Yeah, I could give a couple advices too. One would be try out some popular coding languages. Maybe try some Python or R, and actually try doing some small projects with them and see how you like it, because coding is a very large part of research. And just in general, when you do research, I would advise like to keep your ears open and see what opportunities there are and don't have a closed mind on what you're like, what's going to be your next step, your next postdoc, your next research project. Remember to be guided by your curiosity and what is available there. So don't try to have too much of a very rigid path, and try to like adapt as a function of what opportunities you see happening. That's the advice I would give.
That's some great advice. Thank you so much. Well, we're starting to close to our time here. I think it's ticking away. I wanted to give each of our speakers a last opportunity to have any closing thoughts, but also take the opportunity to plug yourselves so that some of our viewers can actually follow you later on and continue to follow the research of the missions and your own research in particular. I guess we'll start off in order again. So we'll let Jonathan, if you've got any anywhere people can follow you, any plugs you want to give? Any closing thoughts?
So I've got a website where you can find out what's my latest research projects. It's called jgagneastro.com, or you can just type in my name, Astro, in Google, and you're going to find it. So I started writing some blog posts, which are quite long and detailed, but I try to keep them very easy to follow. So if you are, for example, an undergrad who's interested in stellar astrophysics and stellar clusters, there's going to be some stuff in there with videos that I make. So basically, every time we have some nice results coming up, I try to explain them in as much detail as I can while remaining very, very general, so not too technical. So that you can find me there.
Excellent. Thank you very much. We'll throw it to Natalie.
So for my own personal stuff, my website is astropanda.space. If you want to know what the deal with that is, there is an FAQ on the website that explains it. You can also follow me on Twitter at angryastropanda. Also, it is addressed in the FAQ why that is. For IREX, it's exoplanets.ca. You can also find all of our Twitter and Facebook handles on that page. If you want to know more about the Webb telescope, webtelescope.org is the really amazing page that's run by the Space Telescope Science Institute in Baltimore, Maryland. They are the mission control for the science side of things. They also handle Hubble, but there's also a really nice website on the CSA's website on James Webb, who talks more about the Canadian contributions. And stay tuned. This year is going to be the year of Webb, and there are going to be lots of other events that are going to be building up to the launch. And we're hoping to have a huge international live stream at a bunch of different places for the launch. It'll be interesting if it's in the middle of the night. So pajama party in October 2021. So that.
Awesome. And Dr. Nick?
I've got a website. You can Google my name and hopefully you'll find it. There's another Nicolas Cowan who was an actor child actor in Surf Ninjas. So you'll find him first.
That when I was doing my research, it came up.
Yeah, I'm not that cool. I was not in Surf Ninjas or the alligator movie that he was in. I'm the other Nick Cowan. And I'm not on Twitter or any of that stuff, sadly. But if you're interested in the Ariel mission, if you just Google Ariel, you'll again find a lot of random things because it's just like a name. But if you Google Ariel ESA, like European Space Agency, ESA, then you'll find their official website. And there's lots of cool animations and cool stuff like that. And a lot of that just got put on the internet in November because that's when the mission was adopted. So there's a lot of fanfare right around then. So pretty recent activity. Yeah, that's it. Take it easy.
Fantastic. And of course, we have two other speakers we should probably ask. Virginia, do you have any plugs or anything you want to throw out there?
I don't know if anyone. Yeah. Okay. Any plugs? I'm afraid I am nowhere near doing any form of high-level research just yet, but
Do you have a Twitch stream people can follow?
Oh no, I've never used that. But you can follow John Abbott's Space Club. It's mostly for John Abbott students, but they do occasionally do public events along with RASC. And of course, if you want, you can follow RASC Montreal or any other centers across the country.
Fantastic, thank you. And Kareem, do you have anything you'd like to add?
Watching from our audience or on our email list, thank you for joining us. rascmontreal.org. And you'll know that we have 2 public events coming up in February. We have on February 10th, a really nice event put together by Virginia to celebrate Women and Girls in Science, International Day of, and we're going to have a blast discussing women in astronomy and the amazing opportunities available to really aid a lot of women in pursuing this field. And then on February 27th, we have a talk coming up on the Mars science missions. And hopefully Perseverance will have landed successfully on the 18th. And so we could talk about Curiosity to Perseverance, what the progression is going to be. So stay tuned for that and join us on Facebook or on our website for all. Thanks, everyone. We've had a blast. To you.
Well, thank you for that wonderful throw, Kareem. Of course, you can follow us at Guelph Physics on the various socials, be they Twitter, Instagram, Facebook, or YouTube. We do monthly streams with varying types of physics content that we kind of run the gamut of everything. I think we have a medical physics one coming up for February, but stay tuned on here and follow our socials for all types of information, pertinent and otherwise. And I believe we will be, we'll close out this whole thing. Well, first of all, I want to thank everybody who is watching. Thank you so much. That was a blast. This is going to be archives. You can rewatch it again if you want or share with your friends. I want to thank all of our speakers. I want to thank RASC for helping us with this entire thing and making this possible at all. So it's so exciting for us to get this opportunity. But I want to close the whole thing out with our reporter on the street, Mel. She's got a final question to ask our panel, and we'll go with that.
So this was a YouTube question, and maybe we'll just do like a raise your hand type thing. But if given the opportunity to go to space tomorrow, would you say yes? Yeah.
Fantastic. All right, then. Well, and one big final thanks to our man behind the scenes, Saksham Sharma. Thank you so much for putting this on and running all the tech. We couldn't do this without you. Thank you so much, everybody, and hopefully we'll see you next month on another Guelph Physics live stream. Take care, be kind, and remember to science.